Our final topic for wave optics is thin film interference, which, it shouldn't surprise you from the name, is light interference in thin films, like a thin film of gasoline or oil on a puddle of water, or say a thin film of soap between air like you would see in a soap bubble. How this works is very similar to the way the bright and dark fringe patterns happen with double and single slit diffraction, and that is that you have a path length difference between two beams of light that reach your eye. In this particular case, if you have polychromatic light, you have white light made up of a bunch of different colors, you can get constructive or destructive interference of certain colors which cause other colors to emerge. Regents and AP1, you should know this idea. AP2, you've got to do the math. So how does it work? You have a light ray that comes down and hits the first surface, and part of that light is reflected up and away. Some of it, however, is transmitted and refracts inside, changing wavelength as it goes. It then hits the lower surface, reflects, and then refracts back out. Those two light rays are now a different distance apart, and if that distance is half a wavelength for a particular color, you'll get destructive interference. If that difference is a full wavelength, you'll get constructive interference. And again, that goes with multiples: 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, all destructive. 1 wavelength, 2 wavelengths, 3 wavelengths, and so forth, all constructive. If you get constructive interference for green, you'll get green. If you get constructive interference for red, you'll get red. If you get destructive interference for green, then you'll get white minus green, which your brain sees as red, and vice versa. So that's where complementary colors come from in art as well. It's color subtraction from white light. So that's the basics, is just path length difference between the initial reflected ray and the reflected ray that goes through the thin film. Let's zoom in and take a look at the step-by-step process so that we can create the math necessary to solve problems. This isn't on your reference tables, AP2. This is something that you have to come up with understanding the concepts. It's really not that hard, and then once you know them, it's very, very easy to apply. And these are equations that I would recommend that you actually memorize. So here goes.
Okay, so you've got some water. On top of that water, we have some oil. The light comes in, hits the oil, and reflects off. Some of it goes through the oil, bounces off the water, and comes back out. These two interfere, and they have a path length difference of, well, for constructive interference, some multiple m of one wavelength. The wavelength inside the oil isn't the wavelength of the light in air, it's the wavelength of the light in air divided by the index of refraction. So this difference in distance has to be divided by the index of refraction. And here's where things are a little different. When light reflects off of something with a higher index of refraction, it undergoes a change in phase. But when it reflects off of something with a lower index of refraction, it doesn't. A change of phase is the same thing as shifting things by 1/2 of a wavelength, and so that phase change turns this into m plus 1/2. On the bottom surface, does it have a phase change? Well, in this case, we're going to say that the index of refraction of water is less than the index of refraction of the oil, and so the answer is no. Now, the difference in distance is double the thickness, right? So that has to equal m plus 1/2 times lambda over n. Multiply the n over, and we get the equation for thin film interference with one phase change for constructive interference. 2nt equals m plus 1/2 times lambda. Now, if you had two phase changes, that's the same thing as no phase change at all when it comes to difference in wavelengths, right? You shift it by half, you shift it by half again, you're back in phase. Now, if you want destructive interference, you would swap that 1/2 out for a 0. If you had two phase changes, but you also wanted destructive interference, that would swap that 1/2 back in. So really, it's 2nt equals m plus 1/2 times lambda for one phase change and constructive interference. But any change will toggle that 1/2 on or off. And there you go. That's the equation for thin film interference. Let's do an example. Let's calculate the minimum thickness of a soap bubble film that's going to give us constructive interference for 602 nanometer light. So we've got air, and then soap, and then air. Index of refraction of air is 1, the index of refraction of soap is 1.33, and off we go. At the boundary between air and soap, we have a phase change because the index of refraction is greater off the reflected surface. At the boundary of soap to air, we do not, because 1 is less than 1.33. So for one phase change and constructive interference, we say 2nt equals m plus 1/2 times lambda. So for our minimum thickness, m has to be 0, right? And so solving for t, we get lambda over 4n. Plug in 602 nanometers and 1.33, and we end up with 113 nanometers. Done. Suppose we have some clear oil, index of refraction 1.2, sitting on top of some water, and at some point we notice yellow-green light corresponding to 550 nanometers because of constructive thin film interference. Let's figure out our materials and label our indices of refraction. We've got air, and then oil, and then water. That's 1, 1.2, and 1.33. From here, let's figure out our phase changes. At the air-oil boundary, yes. At the oil-water boundary, also yes. In each case, the light is reflecting off of something with a higher index of refraction. So we have two phase changes and constructive interference. That's 2nt equals m lambda. In this case, m has to equal 1, right? For minimum thickness, m can't be 0. The thickness would also be 0. So solving that, we get the thickness is lambda over 2n. Just plug in. Make sure to use the index of refraction of the thin film, which in this case is the oil, 1.2. We get 229 nanometers.
So there you have it. And I just want to point out that even though this is a natural phenomenon, it's something that has a lot of technological applications. In CDs and DVDs, we shine a laser through a thin film of silicon, and based on the thickness of that film, you can get destructive interference a 0 or constructive interference a 1 coming back up, and you can encode data by literally etching or burning away the thickness of that material. So we use it for material storage. We use it in making microchips in order to make that process faster. We use it for all sorts of things that you wouldn't necessarily think would be, ooh, pretty colors on a soap bubble, suddenly applies to modern data storage, or not quite so modern anymore data storage. In any case, there you go. That is thin film interference, and that is the end of wave optics.